is called natural accelerated gradient. Okay, it's proposed by a guy called Yuri Nesterov. Just by this name, you know he's from Russia or Yugoslavian. Okay, so in 1983, again, this one was much earlier than the deep learning. Okay, so it almost always faster. Okay, it's faster than the momentum optimization. Okay, the idea is actually very, very simple. Okay, think about this. Okay, because we want to move toward the lowest location, right? Lowest place on the irregular surface, and usually, okay, the direction you obtained from the next step is more accurate than the direction you obtain from the current step. Okay. Again, let me use the elongated ball as an example. When you are here, what is the momentum you obtain? Remember, the movement direction is somewhere like this, right? So the moving direction is here, right? It's going this way, right? Going downward, right? Okay, but think about this. What is the direction? Where is the lowest location? It's here, right? So direction should be here, right? The correct direction is here, right? But the initial direction is here, right? It's not this direction. It's going down, right? It's more going down. So it's less accurate, right? It's less accurate. But if you try to take it at the next step location, it's going to go this direction, right? So this direction and this direction, which one is more accurate? You may say, oh, both are inaccurate. But isn't the direction you get from the next step, pointing more toward the lowest location, right? Right? If you look at here, okay, the next one going this way, it's going to go even more close to the lowest. I mean, pointing to even, close to the lowest location, and eventually, okay, you can see the direction eventually goes straight to the lowest location, right? So if you are able to take the direction, from the next step, then that gradient direction should be better than the gradient direction that we have currently, right, at the current position. So that's the basic idea. So you see, here, they just try to get the gradient, this gradient, from kind of in the next, in the future location, okay, and use that as the gradient vector, okay, here, okay. The other part pretty much the same as the momentum optimization. The only difference is here. Okay, the other part are pretty much the same, and it turns out it performed like almost always better than the momentum optimization. I mean, here we have another figure. Okay, you can see. I mean, if you take the gradient here, it's pointing to here, but if you take gradient here, okay, well, it's this, well, it's what should I say? This gradient is actually pointing to here. So this gradient, if you use the gradient here, for update, what you are going to get is here. But if you use this gradient for update, you are going to go here. So here or here, this one is supposed to be closer to the lowest location, the optimal location, right? Of course, this is it's more complicated than the elongated ball example I draw there, but you get idea, okay? You get idea, okay? So, yeah, the Nesterov update ends up slightly closer to the optimum, okay? So you may say, oh, this difference between the Nesterov or NAG and the momentum is very small. So why is it like does it make a lot of difference? Yes. Why? Because remember, in deep learning training, okay, it's an iterative, right? Okay, so if you try to earn a little bit better, okay, performance every iteration, so that advantage will be accumulated. So eventually, okay, it will help reduce oscillation and convergence faster. Okay, so this just a little bit advantage turns out to be much better than the momentum optimization. Okay. So if you want to use Nesterov, okay, accelerated gradient optimizer, okay, again, you still use SGD, and but in there, okay, remember, okay, in the Nesterov, okay, you also have the friction, this friction hyperparameter. So you still need to specify, okay, momentum hyperparameter to be 0.9, but you have to set Nesterov to be true in order to let the keras know that you are actually using the NAG, okay. So this is the momentum NAG, and the next one is called ADA grade, okay. For the following couple of optimizers, okay, they are called adaptive optimizers, okay, in the sense that it will automatically adjust the learning rate, okay, it will automatically adjust the learning rate, okay. So again, let's consider elongated ball problem, okay. So gradient descent start by quickly going down the deepest slope and then slowing go down to the bottom of the valley. So basically it's talking about this, right? This line. So this is pretty much a curve, right? This is pretty much a curve. And if you use momentum or NAG, you are still sort of using a curve. I mean, if you are going to a location, okay, going straight obviously is faster than going through a curve, right? Right? Going straight is here, right? Going straight is here, right? So, since going straight is better than going through a curve, that's why we have this ADA grade concept, okay? So, ADA grade algorithm achieve this, okay, by scaling down the gradient vector along the steepest dimension. So it scales down because originally it moved faster on the steepest curve, this direction, right? So it will scale down this way, this thing. So that it will point, toward more close directly to the lowest location. So the formula looks like this. Okay, this S equal to S plus this gradient, multiplied by the gradient. This one, okay, I need to explain this a little bit. Okay, we know this is gradient vector, right? Okay, this is gradient vector, right? But this is, what is this? This is element-wise multiplication. Element-wise multiplication. So it's kind of like what should I say? Like L2. L2. Okay, but we know L2 is root square. Okay, if the gradient vector is like x1, x2, x3. Okay, then what we get there is x1 square plus x2 square plus x3 square. Okay. Well, I'm sorry. Okay, let me take that back. It's x1, x2, x. It's this. This is what we get. What's that? Gradient theta j. Okay, something like this. So it's I probably shouldn't use L2, but you get the idea. It's for each component, it gets like each component is squared. Okay, something like that, and you add that to S to be the next S. Okay, so this S is it's a vector that gets accumulated. Okay, remember this S is also a vector. Starting from the gradient, okay, it gradually accumulates those gradients. And then we have this, theta equal to theta minus eta. Okay, and then we have gradient. But this one is, what is this? Okay, this is element-wise division. Okay, so for each component here, such as x1 square, x2 square, x3, sorry, not square, okay, x1, x2, x3, only x1, x2, x3. This is our gradient, okay? The theta, the gradient theta, j theta. Okay, and divided by S plus epsilon square root. So we add the epsilon to this, and we get the square root of this, and then we divide each component by this. Of course, you may say, oh, then it's x1 divided by kind of like x1. x2 kind of divided by x2, x3 kind of divided by x3, but not exactly that, because S is accumulated. This is accumulated, so it's not exactly just the square of each component. So it's going to be something, plus plus something here. And why do we need to have this epsilon? The reason to have that epsilon is to avoid, okay, because this thing eventually will be, the square root of that eventually will be used for the denominator, right? So we want to avoid dividing by 0, okay? So we introduce a very small epsilon value just to make sure, okay, we are not going to have dividing by 0 issue, okay? But, once you divide, once you divide like s plus x1 squared plus epsilon, the square root of this is again square root of s plus x2 squared plus epsilon, and this one is s plus x3 squared plus epsilon. Okay, so each component gets divided. Gets divided by something like this. Of course, this s is not the fixed value. It's like because originally s gets accumulated from the previous gradients. Okay, but you can see roughly, say, if x2 is larger, it will be divided by a larger value from here, right? It will be divided by a larger value here. Okay, because this x2 squared is larger, right? Okay, so whichever component has a larger value will be scaled down more. Okay, that's the basic idea of LR grade. Of course, we also need to multiply the learning rate and then, everything else. I mean, that's pretty much the same. Okay, so this epsilon. Okay, epsilon is like a smoothing term. Okay, normally we typically set to 10 to the power of negative 10. So it's a very, very small value. It's just there to avoid dividing by 0. Okay, and so pretty much it's it's going to scale down the element, the component larger component. Okay, more than the smaller component. Okay, and so the result is something like this. Okay, so instead of going like in a curve, we are better. We are able to go, much closer to a straight line, to the bottom of this ball. So it will help achieving like a faster convergence. Okay, so that's the basic idea of LR grade. Okay, however, LR grade, often perform well for simple quadratic problem. Okay, but it often stops too early when training neural networks. Okay, the learning rate gets scaled down so much that the algorithm ends up stopping entirely before reaching the global optimum. That's because, here we will add the previous gradient to a new s, right? And then we try to divide element-wisely, the square root of s plus epsilon. And a lot of time, this s, is too big. It's too big. So this scaling down effect is too strong. Because it's too strong. So it will stop the training prematurely. So even though TensorFlow has an LR grade optimizer, you should not use it to train deep neural networks. It may be efficient only for simpler tasks such as linear regression. You could use LR grade. But those are special case. When I say linear regression, I'm not talking about deep learning. I'm talking about like the linear regression for the machine learning. So for deep learning, you probably should avoid using LR grade. So, but you may ask, so why do I need to mention LR grade? Because from the failure of LR grade, we learned that we shouldn't increase the s so quickly, right? We shouldn't increase the s so quickly. So instead of so there's a RMS prop. This algorithm was proposed to fix the issue in the LR grade. Okay, the only difference between eta grade and RMS prop is here. We now use kind of, remember the moving average? Remember moving average that I talked about, the exponential moving average. Now we multiply this previous S by a beta, and this new value we obtain by 1 minus beta. So originally, this S is just a simple accumulation, right? But we found that it grows too quick. This S grows too quick, which caused that the issue. So we now use average. This is actually a moving average, to compute S. So obviously the average should be smaller than the simple accumulation, right? It should be very easy to understand. But at the same time, because we also take this into account, so still the larger element will get scaled down more than the smaller one. That part is still true, but it's just like the scaling down effect is not that strong anymore, It's not that strong anymore. So we normally, this decay rate, we normally set it to be 0.9. Again, a new hyperparameter, but the default value often works well, so you may not need to tune it, So if you want to use RMS prop, optimizer in your program, then basically, there's a RMS prop optimizers, there, You just need to provide the learning rate and this row, this row actually is the beta, in this formula, is the beta in the formula, and except for very, very simple problem, we found that this RMS prop, almost always perform better than eta grade. Eta grade only perform better than the RMS prop in very simple problem, but those simple problems are not deep learning. In deep learning, RMS prop is always better. So it also generally performs better than momentum optimization, natural accelerated gradient. So it was the best optimization algorithm out there. Of many researchers. For many years until Adam optimization, was proposed. So before Adam family, I should say, because Adam is not just one optimization. There are like other, there are a couple of optimization technique, called Adam, Naden, ADAMX. They are all like the family of Adam optimization. But before Adam optimization came along, the RMS prop was the best one to be used. So now it's obviously the time to talk about the Adam, right? So you can imagine, since RMS prop is good, right? So what is Adam then? Well, the Adam, pretty much is a combination of momentum and RMS prop. If you look at the first line, it's like momentum, right? The first line is just like momentum, right? If you look at the second line, well, it looks just like RMS prop, right? So basically, it takes advantage of momentum and RMS prob. Okay, so you may wonder what is the third and the fourth line. Let's not talk about these two lines first. These two lines are there, okay, to fix some issues. But yeah, I mean, those really have, it's not that important, okay. So let's skip these two lines. If you look at the first line, it's momentum. The second line is RMS prob, and then we basically combine those two concepts, okay, in here, okay, because here we have momentum vector, but this momentum gets scaled down by the manner, okay, which is like just like RMS prob. So it's basically a combination of those two optimization, okay. So once you understand that, so what is these two lines? What are these two lines? Because, okay, the M and the S, okay, remember, they are rounding average, right? The M and S are rounding average, right? And at the beginning, the M and the S are zeros, initialized to be 0. So at the beginning, the M and S may be too small. The initial value of M and S may be too small. Okay? So in order to avoid that, so we introduce this third line and the fourth line. Okay? So let me explain the third line, one of these two. You understand, okay? So M will be assigned M, okay, divided by 1 minus beta 1 T. Remember, this beta 1 comes from here. It's the friction, right? It's a friction. That value is normally 0.9 something, right? 0.9 something, right? Remember, the momentum hyperparameter. Okay, so this value, okay. Oh, by the way, T, what is T? T is number of iterations. So at the beginning, of course, T is 1, right? The first iteration, right? Right? T is number of iterations. So at the beginning, the first iteration, T is 1, right? So 0.9 to the power of 1. 1 minus pretty much 0.9, right? So it means what? It means we intentionally, enlarge the value of M, right? We intentionally enlarge the value of M initially. Why do I keep saying initially? Because remember, beta 1 is a value smaller than 1, right? Such as 0.9, right? And this T is iteration. Once the T gets larger, for example, if you have like 10 iterations, 0.9 to the power of 10, it's going to be close to 0, right? Right? That value is going to be quickly going close to 0, right? So when this value go close to 0, what happens? Pretty much you get M equal to M, right? Right? Because the denominator becomes 1, right? When this term is close to 0, 1 minus this term is going to be close to 1. And M will just, this value M will be unchanged, right? So only at the initial stage, M gets enlarged, yes. But after just a couple of iterations, remember in the deep learning training, we have a lot of iterations, right? So after a couple of iterations, pretty much the third formula and the fourth formula do not have much effect at all. Okay, we only want these two lines to enlarge the value of M and S initially, because at the beginning N and S are 0. They are too small, especially when we are doing this running average thing. So we don't want it to be too small, so we intentionally enlarge it a little bit at the beginning. I have to keep saying at the beginning. just at the beginning. Okay, so that's it. That's it. Okay. So I think I already go through all this. Okay, and okay, if you want to use atom, okay, beta 1, okay, which is that friction, okay, the momentum hyperparameter is usually set to be 0.9, and the beta 2, the decay, okay,